All right. Hello, everybody. Welcome to the center of the universe. We're happy to have you all here, both in person and also online. So our presentation tonight is Simon Blouin, and he will talk to us about white dwarf stars. He is from the University of Victoria and has a PhD in physics from the University of Montreal. And with that, I think I'll let you take it away. You've got the laptop all figured out? Yep, okay, great. Yep. Have at her.
Okay, thank you. Okay, good evening, everyone. I'm really glad to be here today to talk to you about my favorite stars, white dwarf stars. So my plan for the next half hour or so is to first just tell you what white dwarf stars actually are. But then I really want to spend most of my time tonight talking to you about how those stars can be used to learn cool stuff about the universe, and especially how they can be used to understand how our galaxy was formed, what exoplanets are made of, and how matter behaves under some of the most extreme conditions we know in the universe. Okay, so what are white dwarf stars? So essentially, white dwarfs are dead stars. So once a star runs out of fuel, it will eventually become a white dwarf. So if we take, for example, our sun, it's currently burning hydrogen in its center. And one day it will run out of hydrogen. It will have burned it all. And at that point, it will start burning helium. And so that will be during its red giant phase, where our sun will inflate, become very big, so big that it will reach the orbit of the Earth, actually. But eventually, it will also run out of helium. And when it does so, then it will lose its outer layers and form a beautiful planetary nebula, like this one. And at the very center of this planetary nebula, there will be a little dense core, which is made of the ashes of all this nuclear burning that our sun will have gone through. And this little pile of ash is what we call a white dwarf. So a white dwarf is mostly made of carbon and oxygen, because that's what you get once you've burned all your hydrogen and your helium. So one of the key characteristics of white dwarfs is that they are very dense objects. So we're talking about something that is about the mass of our sun, but the size of the Earth. So that means that you reach some very, very high densities. So typically, the density in a white dwarf is 1 ton per cubic centimeter. Okay, so just, for comparison, remember that water, for example, is just 1 gram per cubic centimeter. So this is 1 million times denser than water. So this is pretty extreme. So if you were to take a teaspoon of white dwarf, that's about the weight of an adult elephant. So the reason they are so dense is because they are not burning anything. So if they're not burning anything, there is nothing that is pushing outward to counterbalance the gravity that wants the star to collapse into itself. So a white dwarf is what you get when you basically squeeze matter as much as you can. Of course, you can actually squeeze it a bit more, but then if you do that, you will end up with very strange objects. So you could have a neutron star or a black hole if you really compress it more. But for 95% of the stars in our galaxy, they're not massive enough to become black holes. So instead, they will become white dwarfs. So those are very common stars in the sky. Although, because they're very small, they're not visible to the naked eye. So you can see them just if you look at the sky at night, but there are many, many of them. So another key property of white dwarf is that because they've run out of fuel, it means that the only thing they can do for the rest of time is to simply cool down. So it's basically just like a campfire that you just leave there, and it just dies out. And for a star, cooling down means changing its color. So very hot star will have a more white bluish color. And as they become cooler, they will become redder. So you can see the same thing if you look at embers in a campfire. So if you have very hot embers, it will be more white. And then as it dies out, it becomes this darker red color. So this process of going from blue to red for white dwarfs will take many billions of years. So this is a very long process. They are cooling down very, very slowly. Okay, so in essence, what I've just told you is that a white dwarf is a dead star. It's a stellar ember, and it will just cool down for the rest of time. So, I mean, there are stellar cadavers, right? So it's not super sexy, but there are many things that we can learn from them, and that's the main reason why we study them. So I want to go to those three kind of applications of white dwarfs with you tonight. So the first one is that we can use white dwarfs to do what we call galactic archaeology and kind of trace back how our galaxy was formed. The second thing I want to talk about is how we can use white dwarfs to measure the composition of planets in other planetary systems. Down for the rest of time. So this is what this figure here cool, because it means, say we may this white would be 5 billion years old. And that's really cool because that allows us to measure the ages of the stellar populations in which those white dwarfs live. And using that, we can really use white dwarfs a bit like an archaeologist would use carbon-14 to understand what came first, what came after, how long ago, that kind of thing. So in general, it's very, very hard to measure the ages of stars. And just to prove this point, a lot of really good observations of our sun. It's so close, we can monitor it very precisely. And yet, if you look at the sun, there's nothing that you can learn by just by studying the sun that will tell you how old it is. It's basically impossible to measure its age just by looking at it. So the only reason we know how old our sun is because we have meteorites on Earth that we can take into a laboratory, and then we can look at, you can do radioactive dating. And because we know that those meteorites were formed at the same time as our sun, we can then infer that our sun is the same age as those meteorites. So that gives you an idea of because of this continuous cooling, it really. Yes, sure.
So all white dwarfs, so after any stars that die,
yeah,
all become white dwarfs. And all of them will cool at this rate.
So yes, that's a good question. So because stars don't all have the same mass, some will end up forming smaller white dwarfs and some bigger white dwarfs, and that will change the rate at which you cool down here. But the mass of a white dwarf is something we're also able to measure. So this is something we can deal with. And just a clarification, so some stars won't become white dwarf, but it's really a minority. So some will become black holes, right? So here, if we want to do this age dating, a key thing that we need to know is the surface temperature of the star. And of course, you may wonder, well, how do you measure the temperature at the surface of a white dwarf that is light years away? So as I've explained, as the white dwarf cools down, its color changes. And the basic idea is that we can measure what this color is, and then we can translate this color into a temperature. So the way astronomers look at this is we look at what we call spectra. So a spectrum is giving you how bright is the light at different wavelengths or colors. So here, short wavelengths, that's more blue, and long wavelengths, that's more red. So as the white dwarf cools down, this series of curves here is showing you basically how its spectrum is evolving. So initially, the spectrum, it's very intense, it's very high because the white dwarf is very bright when it's young. And then as it cools down, it becomes dimmer and dimmer. So there is less intensity in total. But also you can see that the peak of this curve here is shifting to the right. So it's shifting towards the red. So to measure the temperature of a white dwarf, what we do is that we map out the shape of this spectrum. And the way we do this most of the time is using a very old technique in astronomy, which is known as photometry. So the idea is that you observe your white dwarf, but you put a filter in front of the telescope so that you only have light, the light that goes through is only within a certain range of colors. So for instance, you would do that looking just at blue colors, and then you would look how bright the star is. Then you would repeat that using another filter, another color, so you would know how bright the star is at this other color. And you repeat this process, and in the end, you have mapped out the spectrum of the white dwarf. And from that, by looking at where the peak of this spectrum is, we can calculate the temperature of the white dwarf. And once we get the temperature, well, as I've shown, we can get the age pretty easily. So this is a technique measuring the ages of white dwarfs like that. It's something that has been used for more than 3 decades now. So it's been applied to different population of stars in our galaxy. For example, it's been used to measure the age of our galactic disk, and also to measure the ages of globular clusters, which are very, very old stellar populations inside our galaxy. Yes?
Is it possible for a white dwarf to die?
So that's a very good question. So let me find it. Okay, so as it's cooling down, I guess dying here would be what happens, what happens when you keep cooling down, right? Well, eventually it would become a black dwarf, and that's really when you're completely dead. When you're a black dwarf, you're not emitting light anymore. So you're just, there's really nothing that's happening. But very interestingly, the time it takes to become a black dwarf is longer than the age of our universe. So that means there is no black dwarf yet in our universe. There are still all white dwarfs. They did not have the time to reach that point. But eventually, we predict that, yes, they will die out.
And that would be pure ash form.
Yeah, no, you cannot go.
Like,
Yeah, there's nothing left. Yeah.
How do you measure the age by its temperature?
So here, the idea is that we have, we have computer models that predict the rate at which it would cool down. So the same way you could make a model to predict the rate at which a pot of hot water would cool down, right? And so once we have the temperature, we use those models to transfer that into an age. And in fact, I mean, designing those models, programming those computer codes, that's a big part of what I do as a researcher.
And another question is, how do you measure age of a meteoroid?
Yes.
I guess it is carbon-14 dating.
So it is not carbon-14 because it has, so carbon-14 has a half-life of a couple thousands of years. So it's not really something that's sensitive when you want to measure something that is billions of years old. I don't remember on top of my head which isotopes are used, but you have to use things that will decay, that will have radioactive decay that will last for billions of years. Otherwise, it will all be decayed by the time you measure it. Yes.
So that would
Yes.
like, eventually, like the author producing heat coming up. So would that mean like that eventually after a few billion years of the being of black dwarf will be possible? So for example, like just like assuming that like a million spacecraft could like interact with it without burning up with something, or would it like that be able to happen?
Well, you could, but I don't recommend this because white dwarfs are very dense. And so when you're close to a white dwarf, the gravity is very, very strong. And that tends to rip things apart. Yeah. Okay. Okay, so that was basically what I had to say about galactic archaeology. So the key here, the reason why we're interested into this kind of thing is that once you know how old the galactic disk is, how old the halo is, and the globular clusters, you have kind of the pieces of the puzzle that you can start putting together to figure out how exactly our galaxy was formed. So this is kind of the reason why this kind of work is important. Okay, reason number 2 to study white dwarfs, exoplanets. So as you know, exoplanets, those are planets that are orbiting stars other than our sun. And now you may think, well, what do dead stars have to do with exoplanets? Well, let's take the example of our sun. So currently, we have a nice, stable system of planets that is orbiting around our sun with asteroids and comets and whatnot. But eventually, our sun will become a red giant stars. And when it becomes a red giant, it will have very strong stellar winds, which means that it will expel a lot of mass in our solar system. It will lose mass. And if our sun loses mass, well, that will affect the orbits of the planets in our solar system, because the reason our planets orbit around our sun, of course, is because of the gravitational attraction of our sun. So if you start removing mass from the sun, well, you're changing the gravitational attraction. So if you change the gravitational pull, the orbits of the planets in our solar system will change. So some collisions can occur, that kind of thing. So it will lead to a whole lot of instabilities. And so we predict that you will have planets or asteroids or comets that will start crashing onto our sun. And this will continue by the time our sun will have become a white dwarf. So if someone living in another planetary system was looking at our sun by that time, it could see, if it looks at the light that is emitted by our sun that will have become a white dwarf, it could see the signature of all the things in our solar system that will have crashed onto this white dwarf. And this means, of course, that we can do the same thing. So we can look at white dwarfs in our galaxy, and we can look at white dwarfs that are being polluted by those planetary debris. Yes, question. and a very so in 4.5 or 5 billion years. So in a very long time. Yes. Okay. So the reason why it's really cool that those white dwarfs get polluted by those debris is because by then looking at the light from those white dwarfs, we can find out the composition of those planets. So the way this works is using this technique known as spectroscopy, which is something that, for example, a chemist could use in the lab if they have some sample of some substance that they want to identify. So the idea is that you shine a light through your sample, and then you separate the light into its different colors using a prism or something that does the same job as a prism. And then what you get is a spectrum. And in the spectrum, you have some little dark lines. And those dark lines, they're called absorption lines. And they are basically a barcode for the substance that you're studying. So every chemical species has its own barcode like this. So if you get the barcode, you can say, oh, that was water or whatever. So with our polluted white dwarfs, we basically have the same setup, right? Because now my white dwarf is playing the role of my source of light. Then on my white dwarf, I have a little smear of dust from planets, comets, or asteroids that crashed onto the white dwarf. So the light is going through this material, and I'm then taking the spectrum from that. And so the absorption lines that I see here, they will tell me what those rocky debris are made of. And so using this technique, we've been able to determine the composition of exoplanets that crashed onto their white dwarfs. So the last 6 bars here, they're giving you the composition that we've measured in those exoplanets. So you can see oxygen, iron, magnesium, silicon, calcium, and aluminum. And those are all the elements that make up rocks on the Earth. So you can see if you compare the composition of those last 6 bars to, for example, here you have the composition of the Earth. Well, you can see that it's pretty similar, right? And so this is really interesting because it's telling us that the way planets are formed in exoplanetary system is actually very similar to what went on in our own solar system. Of course, there are exceptions. So sometimes we find compositions that don't match anything we know in our own solar system. And then the game is to try to figure out, well, how could you end up with something like that? And here I should stress that this is the only method we have today to determine the composition of planets outside our solar system. And this is something that we started doing just about 10 years ago. So one reason it took some time before we started to do this kind of analysis is because, of course, we first had to figure out that those lines that we see here are actually the signature of planetary debris that crashed on the white dwarf. Yes.
Because of some the lines are similar to the Earth.
Yeah.
Does that mean like in many years we might be able to live on those planets?
So this is telling you how what the rocks on those planets are made of. So we're missing a lot of information from this. So you would also want to know, how close those planets are to the star and that kind of thing. But there's actually a bigger caveat. So remember, those are pieces of planets that crashed into the white dwarf. So, that's not something you could go live. They are dead planets on a dead star. But it's still interesting because, we can look at those and infer from that the other planets are probably also like, something that looks like this, pretty much.
Find the composition of the debris hitting white dwarfs, so you couldn't use this on a planet that's not typical.
Exactly. So you could, one thing you can do that is really a hot area of research right now is that you could be able to determine the composition of the atmosphere of those planets, but everything below, the ground, no, there's no way you can do it. And it's something that's actually very important because the composition of the rocks that made up a planet, they tell you, can you have plate tectonics, volcanism, and those are all things we think are key to the emergence of life. So that's something interesting. Yes?
So I guess dead planets crashing into white dwarfs, the gravitational pull of the white dwarf can alter some of the surrounding space.
What do you mean by space?
Well, just it's pulling things into
Yes.
its,
Yeah.
through its intense gravity.
Yeah, exactly. And actually, yeah, I will come to that very shortly. One thing I absolutely have to mention before that is that it turns out that white dwarfs provided us with the in 1970. So this proof came from this white dwarf Van Manen 2, which is the closest solitary white dwarf to our sun. So some white dwarfs are closer, but they are in systems with 2 stars. So this is the closest that is alone. And in this spectrum taken in 1917, you can see here 2 little dips, and those are absorption lines from calcium. And we now know that the only way we can explain calcium lines in a star like this is nation. So it's pretty cool to know that the proof of the existence of planets outside our solar system was sitting there in those archives for more than a century. Okay, now a key portion of the story that I've omitted so far is how can we be sure that those little So there are many lines of evidence that point into this direction, and it's now unanimous in the community that this is the right explanation. So the first one, and this will probably answer your question, is that the planets or asteroids or comets that crash into the white dwarf, they don't just crash directly like a meteorite hitting the Earth. So before reaching the white dwarf, because the gravity is so strong, it will rip apart as approaching the white dwarf, and that will form a what we call an accretion disk. So it's basically just a big disk of dust and gas that is orbiting the white dwarf, and that is slowly emptying onto the white dwarf itself. And
Similar to the rings of like Saturn.
yeah, exactly, very similar. Yes. Yes, I don't recommend. Yes. So the gravity, the gravity at the surface of a white dwarf is really, really strong. So it just wants to pull you in, but if you're close enough, it will pull harder on your feet than on your upper body. So then it means that your body we're able to, so we cannot image them. So this is just an artist's impression. We cannot see something like that, but we can see their signature because the disk itself is much cooler than the white dwarf. If you take a spectrum, well, you will see at very long wavelengths. So if you go after red colors, then you have infrared. So in the infrared, we see a lot of light coming out from those stars, and the only way is that every time we see it, that come from rock forming elements. So everything, matches very well with our expectations. Another more direct proof that this is the right explanation is that in some cases, if we're very lucky, we can observe a transit. So a transit is simply when the planetary body is passing in front of the white dwarf, but you have to get just the right configuration, right? You have to be looking at the white dwarf, and then by chance, this planetary body that is, slowly falling to the white dwarf, it's passing just in front, between the white dwarf and our telescope. And so what you see here, so the black dots, it's actual data, and it's showing you how bright this particular white dwarf is as a function of time. And so you see it's the same brightness and brightness and brightness, and then boom, it falls by about 50%, and then it slowly goes back up. And the explanation is that there's something like this passing in front of it. So there's a kind of comet that is slowly disintegrating. So when it passes in front of the white dwarf, initially, so imagine this side passes first, well, it will very sharply drop the luminosity. But then on the other side, it doesn't go back up as sharply because you have this tail of debris behind. Okay, so this region here where it's just slowly, the brightness is going up slowly, it's because we're observing through this tail of debris behind the comet that is being accreted. So this is actually a very cool star because it's the only one for which we can see live the accretion of this planet. So it's a really good opportunity to learn about how those things actually happen. Okay, third and final reason to study white dwarfs, and one that's very close to my heart, is that I've said that white dwarfs, they're ridiculously dense, 1 ton per milliliter, and so those are conditions we cannot reach on Earth, and so there's a lot of question about what happens to atoms and like that when you compress them to such high densities. So this is a picture of the national, and what this is a big sphere in which you have 180 super powerful lasers, and what they do with that is that they send all those lasers at the same time on a very small target of just 1 millimeter, and by doing that you can reach super high pressures. So 1 million times the pressure of the atmosphere on Earth. But it turns out that if you do that, you're just barely scratching under the surface of a white dwarf. So we can reach with that the conditions that we have just about 1 kilometer below the surface of a white dwarf. But what we want to know is what happens at the center of the white dwarf, where the most crazy extreme things are happening. And one of those crazy things is that actually, as white dwarfs cool down, they eventually freeze. And this might be surprising because, white dwarfs stars are hot. Stars are generally made of plasma. This is not something, it's not a solid, it's something, it's a gas, it's something that's moving all around. So how can you freeze like that? So what happens is that in stars, so matter is under this phase that's known as plasma. So plasma is when you have just bare atomic nuclei. So they don't have their electrons orbiting around them anymore. The electrons are just floating everywhere. And those little nuclei, they are positively charged. So this means they want to repulse each other. And that's why here in this little movie, so this is from actual calculations, you can see that it looks basically like a liquid, but the little nuclei, the little spheres here, they're never touching each other. They're repulsing each other. As a white dwarf cools down, they have less and less energy to move around, right? When you decrease the temperature, there's less energy for things to move around. So it starts looking more like peanut butter or something like that. It just barely moves around. But then the very cool stuff happens here. When you're very cold, then they basically stop moving and they freeze into very specific positions, right? This is not random. This is forming a crystal. So when white dwarfs become old enough, they freeze into a big crystal of carbon and oxygen. And we can actually see the signature of those stars freezing. So to understand how we can do that, it's worth thinking about what happens if you take a glass of water and put it in a freezer. So if you take a glass of water at room temperature, place it in your freezer, and you measure its temperature, well, you will see, of course, it will drop. When it reaches 0 degrees, it will start to freeze. But what you will see that it will stay at 0 degree, until it's completely frozen. So there is kind of this and heat. So all your little water molecules, they have to stop moving. So they have this energy that they had for moving around, they have to expel it. And that's why it cools down more slowly. And then once you're completely frozen, you can continue cooling down. So the same thing happens in white dwarfs. When they are in the process of freezing, their temperature remains essentially constant. And we can see the signature of that in astronomical observations. So this is really, cutting edge science I'm talking to you about. So this is something that we discovered just 2 years ago. So this is the Gaia Satellite, which is a space telescope from the European Space Agency. And what this space telescope does is that it's just measuring very precisely the brightness and position of billions of stars in our galaxy. And here on the left, you have a more complicated figure. It's the most complicated figure of my talk. I apologize. I'll do my best to explain it as well as I can. Every little circle here, the little black dots, it's one white dwarf. And so they are placed on this diagram so that the ones at the top here, those are the very young ones. Those are the bright, hot ones. And as they become older, they cool down following this track here until they're very cool and faint and old. So that's why they're all clustered around this sequence. That's the white dwarf evolution track. But the intriguing thing that we found is that here you see that there is kind of they're forming another sequence here. There's another line. And so this is not something we were expecting at first, but it turns out this is exactly where we predict that white dwarfs are in the process of freezing. And if you're in the process of freezing, remember, you're staying at the same temperature. So the white dwarfs that are coming here, they just sit there for billions of years. They stay there for a long time. So this is like a traffic jam of white dwarfs. They're just all jammed there while they're freezing. So we're seeing a pileup or, an overabundance, a traffic jam of white dwarfs in this location. So white dwarf freezing was predicted some 60 years ago, but it's only 2 years ago that we have observational that is actually something that's happened. Test whether we understand what's going on inside those stars. Yes. No, there are much more than that. So those are just the ones in what we call our solar neighborhood. So a couple dozen light years from our sun, but there are much more than that. Yeah. Yes.
You're including color spectrum that had like the hottest white dwarf being the top and whitish.
Yes. Yes.
Has that happened from that right corner?
Yes. So here they're blue and here they're red.
Okay, so that's
yeah. Yes.
They're actually freezing when they're kind of in the middle.
Yes, exactly. Yes. Yeah. Okay, so that's all I had for you. So I just, if you have 2 takeaways from tonight. So the first one is that the white dwarf is a dead star that's just cooling down for the rest of time. And the second takeaway is that those are stars that we can use to figure out how our galaxy was formed, what exoplanets are made of, and how matter behaves under crazy conditions. So thank you very much. And of course, I'll be happy to take any more questions you may have. Yes.
First of all, thanks for the talk. That was really interesting. So about 5% of stars have a mass that exceeds formation to a white dwarf.
Yeah, correct.
They form into black holes.
or neutron stars. Yeah.
So what does that mean exactly? Does that mean that the universe can't handle more than that level of density, or?
Good question. So it gets into, yeah. Okay, so if what happens is that if you have more mass than that, the reason white dwarfs have the size they are is because the electrons inside the white dwarfs, they don't have any more energy levels where to go. And this, I mean, it's really hard to explain that without going into quantum mechanics. But basically, there is no room for more matter. So if you try to squeeze it more, then what happens is that the electrons and the protons will merge together to form neutrons. And well,
The sun starts to fill with helium. Does it have a stronger gravitational pull?
good question. So no, it won't have a stronger gravitational pull because its mass, I mean, it will change its size, right? But the mass will stay the same, except that it will have this wind. But let's say its mass stays the same. And if the mass stays the same, well, the mass is what we care about for gravity. It's really the mass that matters, not the size. What is left over after?
When the white dwarf starts to cool down?
You mean what's inside the white dwarf?
Yeah.
Yeah. So it's in most cases it's carbon and oxygen because that's what you get when you burn helium. But some very massive white dwarf will have oxygen and neon. Yes. That answer your question? Or?
Yes.
Okay. Yes.
So you mentioned that white dwarfs are not visible. We cannot visually see them like all other stars.
With the naked eye, but with a telescope, of course, you can.
So what's the most common method to explore these white dwarfs, their location? Like, how does one really explore them?
If you want to do it yourself, or
at the research level as well. Yeah.
yeah. Well, so how we find white dwarf is mostly using their colors. So most of them, the easiest to find are the young ones that will be this bluish color, and so they have very different properties. If you measure this spectrum, it really looks different from other stars. And one thing I should also say, if I find my slide, is that this spectrum, it looks very different for a white dwarf than for other stars, and it's very important because the spectrum that I'm showing here is actually the spectrum of the sun. Okay, and you can see there are many lines here. If you take the spectrum of a white dwarf, you will have very few lines, and the reason for that is that because the white dwarf has such a strong gravity, all the elements just want to sink at the center. So all you get at the surface that we can actually see is just hydrogen or helium. So just very few elements. So that's why when we add planet stuff on it, we know it has to come from elsewhere, right? But that also means that if you measure a spectrum from a star and you only see hydrogen or only see helium, you know it's a white dwarf, because otherwise you will have all sort of other stuff in there. So in the spectrum of the sun, we see calcium, sodium, potassium, so many things. Yeah.
Thank you.
Well, I'm a theorist, so I don't go. But I mean, I use pretty cool supercomputers, though. So yeah. Well, thank you, everyone, and.
Okay, hi everybody. It's Don here, and I'm going to start off with the next part of this, and hopefully make myself, I see I'm in the spotlight now. That's great. Thank you. And Amy and I are going to do a couple of things tonight. I'm going to just talk about what's up in the sky, and then we're going to try to show a video. So this is something new. So Amy's being very brave in attempting this. I haven't figured it out yet, but I think she has, so we'll give that a shot. And it's a fairly short video, but I'm sure it'll be interesting. So Amy, what is the title of it? I can get you to pipe up if you're handy here.
Sorry, I'm trying to remember. It's the story of. No, I can't. I'll have to look it up. Sorry,
Okay,
I can't remember.
fine. That's fine. We'll figure. You have some time to figure.
It'll be
it
a
out.
surprise.
It'll be a surprise video. Great. Okay. So in the meantime, I'm going to talk a little bit about what's up in the sky, as I said, and this is for today, for June 4th, and for really the next 2 weeks. So sunset is 9:10 p.m. tonight, and sunrise is 5:12 a.m. And of course, with the sunset of 9:10 p.m. And darkness not happening until an hour and a half later, it really doesn't start to get dark until after 10:30, fully dark. And so, but we're going to talk first about the morning sky here, because that's what's really of interest right now. And what we're seeing here, I'm just going to move this out of the way here for myself. We're seeing the morning sky at about 4:05 in the morning. And you can see that there's some bright planets visible. Venus is down quite low to the horizon. And then we can see Mars and Jupiter. And we're already into twilight at that time, because of course we're within an hour and a half of sunrise. And if we just advance this a little bit more, if you were lucky and say near the seaside and so on, you might be able to see Mercury coming up, but it's pretty unlikely because it's lost in the glow. But nevertheless, you can see that the planets are all strung out in a line. And if I just move this out of the way and go and actually just shift this over a little bit, you can see that Saturn is over there as well. So the two really bright planets that you'll see here are Saturn and Venus. Those will be the standouts in the morning sky. And so let's talk a little bit more about what's up in the sky. So June 7th is the first quarter moon, and June 14th is the full moon. And as you can see, the difference appears to be about 7 days between each of these major phases. And the lunar month, the time for a phase to repeat, for example, the time between successive full moons is 29.53 days. So the time between each of the major phases is a little bit more than a week. It's about 7.3 days. And as a reminder, the names for the phases are a curious mix of appearance and position in the orbit, or time in the lunar month. And so the first and last quarter correspond to what look like a half moon, but actually refer to the position in the lunar orbit and in the lunar month. So at first quarter moon, the moon is 1/4 of the way through its orbit and has also completed the first quarter of the lunar month. And last quarter means the moon has 1/4 of its orbit to complete, or is entering the last quarter of the lunar month. However, at full moon, at the halfway point, we see all of the moon illuminated. So if we were talking about the lunar orbit or month, we would call it half moon. But just imagine how confusing that would be to people if we did that. I don't think people would accept it. And the terms crescent are also descriptive enough, but we can say more about them. During the first quarter of the lunar month, we refer to the crescent as waxing, which conjures up the images of candle wax building up. And we also refer to gibbous phase between quarter and full moon. And after full, we refer to the moon as waning in both the gibbous and crescent phases. So when the moon is closest to the sun in the sky, we refer to that as new moon, as if the moon were being reborn. But of course, if we're being much more descriptive, we might call it no moon because we can't see one in the sky. So it is a rather confusing thing, and we still hear people talking about half moons and so on, without knowing the reasons behind the names of the phases. So as the nights get shorter and the sun gets higher in the sky, you'll also likely notice the moon in the daytime sky this month. especially around first and last quarter. And one other thing that you might not be aware of is that over the course of time, the moon is the moon the phase appears to change slightly as you were looking at the moon from over the course of a night. And if you could actually measure the phase precisely, you would see that over the course of a night, it wouldn't be waxing or waning evenly, but would appear to kind of oscillate a little bit. And that's owing to our changing vantage point relative to the moon. But it's such a subtle thing that you wouldn't really be able to notice it without making precise measurements. One thing to note this month is how low the moon is in the sky near full. And what I'm going to do is just advance the time here to the morning of the 14th and just make it a little bit earlier and move this out of the way. And there you can see the moon is pretty much due south. And just play with the time a little bit, make it a little bit closer to 1 o'clock. And of course, this is daylight time. So it'll be due south just around 1 o'clock. If you're on standard time, it would be right at midnight. But the moon is actually very low in the sky at this time of the year. It's just 13 degrees off the horizon at its highest at this time. And so what we're actually seeing is the moon light filtered through about almost 4 times as much air as if it was directly overhead. So it's actually only about 2/3 the brightness that it would be in the winter time when it's much higher in the sky, because so much of the light is being filtered out, and also because it's passing through so much more air, it's going to appear redder because the blue light that's reflected off of the moon from the sun is also being scattered out. So it's going to look a bit more reddish. And the other thing to note at this time of the year is that the moon illusion is very strong because the moon is so low in the sky. And so the moon will actually appear to look rather large, but it's actually not that much bigger. It's just a psychological trick. But what I like to remember at this time of the year is that the moon is opposite to the sun in the sky. So when we see the moon really low like this, remember that that's how high the sun is in the sky approximately in the winter time. So around the winter solstice. So it's approximately that height in the sky. So the sun in the winter time really doesn't get very high in the sky here, as I'm sure you've noticed. Finally, just one last thing. See if I can move it a little bit earlier in the night here. And oops, don't want to make it too much earlier. But we can see that, I'll just see if I can get some constellations appearing here. And we can see that the summer sky is starting to appear over on the eastern horizon as in the late evening. And unfortunately, you can't really see the Milky Way too well because it's so low down. And that, again, refers to that dimming effect plus all the scattering of street lights and so on in the sky. But if you could get to a nice dark location, you would actually be able to see the sky quite well. Let me see if I can just move something out of the way here so I can show you what that would be like if we could take the atmosphere away, and there we could see that the Milky Way would reveal itself. One other thing I can just throw in here is that you heard about the black hole that was imaged using a new technique using millimeter wave telescopes, a cooperative worldwide effort, and hopefully you saw that in the last month. But the position of the black hole is actually below the horizon this month. We'll have to wait until July for it to be above the horizon if you were just wanting to gaze off in that direction and think about it. So right now it would be just below the horizon during the middle of the night. So I think that's about all I want to share at this point. And Amy, if you're ready, we can try to move on to showing the film. So bear with us, everybody. This is going to be an experiment.
I'm going to try. Technology is not always my friend. Let's see how we make out here.
So let me see if I can put the spotlight on you. Calvin, are you still there? Maybe you can help us with the spotlight.
I just asked him to come back to it, so he might be there.
Okay. Nice to see you here, Peter, as well as Jim and Betty. Thanks for bearing with us. Oh, there we go. Okay, I'll be quiet now. Hopefully we'll get some audio.
Hi, I'm Melissa. I'm with the FDAO, Friends of the Dominion Astrophysical Observatory. I'm 11, and I'm learning about constellations myself. Constellations are like a dot to dot in the sky. When telescopes were invented, it helped astronomers see more in the sky. Eventually, they made a map of the sky with 88 official constellations. 1922, it's like a picture in the sky. But even though you may just see a whole bunch of stars, connect some of them, you might get something like a unicorn. But there are so many more constellations. I'm so looking forward to you guys joining me and learning about the constellation. Once there was a poor shepherd named Arius. One day, Poseidon, Zeus, and Hermes came to his house. Arius didn't know that they were gods. But yet he was so generous, he killed his last ox to feed them a meal. While they were leaving, they granted Arius one wish. His one wish was to have a child. So they said, bury the animal hide from our meal and then pee on it. Well, personally, I don't get why you would pee on animal hide, but it's just how the story goes. And 9 months later, there was a baby. Arius named this baby Orion. Orion grew up to be strong, tall, and for some odd reason in all the stories he's described as handsome. Don't know why, just how the story goes. When King Enopian heard of Orion, he asked Orion to slay all the animals on Chios. So Orion did. He got so sure of himself that he said, I am going to slay all the animals in the world. Which made Gaia, the earth goddess, extremely mad. So she sent a ginormous Scorpio to kill Orion. Well, when Scorpius found Orion, Orion tried to fight it, and then Orion realized he can't kill a scorpion with a sword in his strength, so he ran for his life. But sadly, the scorpion stung him to his death. Gaia put the scorpion in the sky to remind Earth to respect the environment and the animals, and then she put Orion in the sky to always be chased by scorpions. Thank you for listening. Please like and subscribe. Follow us on Facebook, Instagram, and Twitter. See you all next time. Bye. Do you know how to find Orion? In the northern hemisphere, Orion is a winter constellation.
Is this another part?
Yeah.
Right after sunset on Happy stargazing.
I think it actually works. Could everyone hear it?
It was pretty faint. You could, if people would like to turn their microphones on, we can
Yeah.
have a little discussion about it. Yeah, I think I could hear it when I had the speaker up, but if it was just through my computer speaker, it was a little bit hard to hear.
Yeah, I also was, you saw a couple times I tried to raise the
We're all
volume a
doing it.
bit. Now we have the mics. When we do it again, I would mic her. Definitely.
Absolutely.
Yeah.
Yeah. So we get an idea. I think we have a good idea of the audio level it needs to be, but it's a great first start. Video looked great and everything. It's nice to actually show kind of like a point of view from inside the planetarium like that. I think that was really cool.
Yes.
And
That's-
so great to get one of our young members involved like that.
Yes.
So way to go, Alyssa.
I completely agree. That's a wonderful thing to do. Well done.
We will have more of those.
Yeah, awesome. Something to look forward to. Well, I think we're going to end the presentation here for tonight, but thanks for bearing with us. We're still working out a few bugs, as you can tell, but we're getting there. So, and thanks for being the mastermind for all this, Calvin. That's
Yes,
what's that,
always.
3 for 3 you managed to get working for us? That's
Yep. Oh, no one spotlighted. There we go. Yeah.
Okay.
All right. Yeah. Thanks for sticking out with us, guys. It was a good talk, actually.
Yes, it was great.
Yes,
Good.
it was.
Looking up. Yes, very good. Job.
Okay, thank you. Good
All
night.
right. Good
Thank
night,
you.
everybody.
Good night.